I'm going to talk about parametrization. In particular, I'm going to explain why you put this gamma prime of t in. And I'm going to start with an algebraic explanation, and then I'll give you a little more intuitive explanation. And that is, so in calculus, you may have encountered an integral at some point like this. X over x squared plus 1 dx. The way we typically solve this is we let u equal x squared plus 1. Du is equal to 2x dx, and 1/2 du is equal to x dx. So what do we have to do? We can just replace it. I won't even talk about the limits of integration here, but you've got x dx is equal to 1/2 du, and x squared plus 1 is equal to u. And now this is pretty easy. Integral is 1/2 natural log of u from the limits of integration, and so on and so forth. Well, in one sense, we're going to do the same thing, right? We're going to do a z substitution. We can let z equal the parametrization, which allows us to replace this z here with a gamma of t. But we also have this dz that we need to get rid of. So I can take the derivative of both sides, and here I have to use the chain rule. The derivative of this is equal to gamma prime of t times the derivative of the inside, which is just dt. So algebraically, we're going to replace purple, right? This dt turns into this entire thing. And that's algebraically why we might want to do that, is it's a lot like u substitutions. On the other hand, more intuitively, I'm going to look at these two parametrizations of the integral 0, 1, or the interval 0 to 1. One is I'm just going to let u gamma of t equal t, where t goes from 0 to 1. And another one I'm going to have it be t squared from 0 to 1. Now, the point of an integral is essentially we want to add up all the different function values here. And that's impossible to do since they're an infinite number, but the way we do it is we chop it up into fine little pieces and we kind of multiply, we turn it into something akin to a rectangle. This is 4 dimensions, so it doesn't quite work. But I want you to pay close attention to how I draw this, right? Gamma of t equals t means that I'm going to draw this kind of in a steady rate from there to there, because the velocity here is constant, the derivative is just 1. So in some sense, I'm going to spend an equal amount of time over every single point. So I'm going to multiply the function value by 1 because I'm spending an equal amount of time over every point. Let's contrast that with over here. Now I have t squared. Here's how I draw t squared. Starts off really slowly, and then gets faster and faster and faster. See that again. Starts off really slowly, and then gets faster and faster and faster. Right? Because t squared, the velocity of that is going to be 2t. The farther I go right, the faster I go. Which means, at this point here, I'm going to spend not a lot of time over it. And over here, I'm going to spend a lot of time over it, because when I draw it, I go, I'm going slowly. Oh, I'm hovering over that point a lot, but now I go fast, and I barely spend any time at all over there. So to compensate for that, we want to multiply the function value times the derivative. So here the derivative is really high, which means I don't spend much time over it. So I take the function value and multiply it by more to compensate for the fact that I don't spend much time over it. Whereas over here, the derivative is really small. So I'm going to spend a lot of time over it. So I'm going to multiply it by this relatively small number to kind of compensate for the fact that I dwelled on this part for a little too long. So that's kind of an intuitive idea on how to understand it. And this was an algebraic way. Thank you.